Hello there. We are the Steel Bridge team from Cornell University. My name is Gregory, and joining me today are a few of my teammates. Introduce yourselves.
Hi, my name is Jenna.
Hello, my name is Thomas.
Hi, I'm Miyuki.
Today, we plan on guiding you through the design, construction, and analysis of our bridge.
To start things off, here's our overall bridge design. The bridge is an upper truss bridge that is 21.5 feet long and 4 feet 2.5 inches tall. It utilizes a space frame designed with an intricate weave and incorporates worn trussing to tie everything together, allowing for an overall aesthetic shape. To understand how we got here, let's talk about the design process that eventually produced this final bridge design. At the beginning of the year, our team broke up into 4 groups of 3 to 4 members. These 4 groups of people design, analyze with Massstand 2, and pitch potential ideas for the overall bridge shape we would spend the rest of our time working on. The team then voted on the best bridge design shape based on the factors of fabricability, aesthetics, constructability, along with keeping the overarching principles of minimizing deflections and weight in mind. This current design received the most votes because it had the potential to produce amazingly low deflections due to the space frame and large upper truss height. Each side of the bridge can be broken down into roughly 6 members, which makes constructing over the river significantly easier than with a 7-member breakdown. After picking the current design as the overall shape of the bridge, our groups designed and presented a wide array of ideas for connections. We took ideas from each group and incorporated them into the suite of connections that we used for the bridge. Soon after, the team then worked together to CAD the entire bridge through Autodesk Fusion 360, resulting in this bridge that we are presenting to you right now.
While we are proud of our bridge, we do acknowledge some of the downsides of this particular bridge design. Yes, space frames do provide additional structural support, but they are notoriously difficult to create. Our CAD files do have perfect measurements, yes, but in the machine shop, we do not. The space frame's complexity is possible to produce in-house, but it would nonetheless be time-consuming. Another downside of this bridge is its weight. At 278 pounds, this places the bridge on the heavier end of the spectrum and incurs more costs for the additional weight. Heavier members also, in theory, make it slightly more difficult for builders to construct the bridge, because outstretching one's arms can be more strenuous with heavier objects, especially when constructing over the river.
Of course, we do not deliberately allow these disadvantages to slide if they are not counterbalanced by advantages. The bridge's heavy weight is offset by its extremely low deflections. Having trussing, the space frame, lower laterals, and even legs all contribute to the structural strength of the bridge. These low deflections justify the large weight because the structural cost of the deflections greatly outweighs the structural cost of the additional weight. Other aspects of the bridge also provide advantages in constructability, in particular the numerous boltless connections in the space frame. Of the 3 stringer tubes in the space frame, we decided to place the bolted connections on the outer tube because in Massstand 2 modeling it revealed that there are greater stresses on the outer tube than the inner, and it also makes the bolting more accessible for construction. The connection between the upper cord members utilizes plate and inner tubing to bring together both round and square tube. There is already a pre-welded peg incorporated into this connection. The main strength of this connection is that it connects 4 members with only a single bolt. So as you can see, this bridge is also advantageous because these innovative connections allow for an easier construction experience for all builders.
Speaking of construction, designing the bridge is one thing, but getting it to come together is another thing. We'll explain some of the strategies that we would have used for construction if the bridge was physically built. The plan is to have 4 builders in total, 2 on the east end of the bridge and 2 on the west end of the bridge. Each pair will have a designated builder that primarily travels back and forth between the staging yard and the construction zone. This is to transport the members of the bridge. The other builder of each pair will focus on connecting the bridge and securing any bolted connections. East end builders will start building the bridge on the south side and west end builders on the north side. They will meet by the river once the bridge stringers are constructed to be long enough to cross the river. At this point, a builder from each side can extend an arm to grab the respective stringers on the opposite side and continue building off them. Connecting the stringers together is expected to take a short amount of time because of the boltless dovetail connection between space frame members, which allows space frame members to remain stable on its own without moving through first. The builders will then start constructing the upper course of the bridge with a similar building strategy as with building the stringers. Thanks to our construction-friendly connection design, All of our upper chord connections only require a bolt and a peg to connect and can also stay in place without bolting through first, which will further help speed up with construction. Once the upper chords are constructed, we will finish up by connecting the remaining laterals.
One of the possible difficulties that we considered was reaching out across the wide river to hold incoming stringers from the other side of the bridge. We calculated distances and decided to section our bridge into 6 members, which would allow for construction within reasonable reach limits. With our strategies and construction sequence, we believe we will be able to construct this bridge in about 14 minutes, with 2 of those minutes accounting for particular historically experienced delays. We are confident in this estimation because we have many boltless and single bolt connections, which will significantly speed up the construction process.
A construction-friendly bridge and a well-thought-out construction plan undoubtedly will help our builders perform well. But what about the performance of the bridge itself? Through modeling the bridge in Autodesk Fusion 360 and applying load cases in the program's simulation feature, we were able to procure a thorough understanding of the expected behavior of the bridge under loading conditions. First and foremost, perhaps the most pressing question that a bridge proposal must address is whether it'll fail or not. Our analysis indicated that our bridge design will not fail and is indeed stable. Subjecting the bridge to the specified 50-pound force lateral load case caused the bridge to only sway 0.0003 inches horizontally. When loaded with the 6 specified load cases, the bridge vertically deflected at D1 and D2 at an average of 0.153 inches aggregate.
In our analysis of vertical deflections, our methodology involved testing the bridge design against the 6 load cases included in the design specification. For each load case, we applied a distributed load in the location specified for the load case and ran simulations to determine the deflections at the D1 and D2 locations. We conducted our lateral load analysis in a similar manner. Our analysis concluded that the average deflection of the D1 and D2 locations were approximately 0.08 inches and 0.073 inches respectively. Load case 4 presented us with the lowest aggregate deflection of about 0.13 inches, whereas load case 3 presented us with the highest of about 0.182 inches. These phenomenally low deflection values drastically reduced the estimated structural cost of our bridge. Using our lowest and highest aggregate deflection, our total estimated structural cost ranges between $1.23 million and $1.4 million. So in terms of deflection, our analysis of the bridge design indicates that all seems to be going well. In terms of shear and bending moment, notice that the largest magnitude shear force is a little under 3,000 pound-foot, whereas the largest magnitude bending moment is about 16.4 kips-foot.
As with most analysis, there are limitations to our analysis in Fusion. In Fusion, it models all of our connections as welded connections, while in reality, many of them are pin connections. In addition, the way the analysis was performed was that each leg was fixed on the side facing into the bridge. While this was to make sure that the bridge's legs would not deflect into the ground, the bridge's legs in real-life situation would not have been fixed and would be free to slide on the ground when applying loading. But Fusion would not allow a simulation to happen without fixed constraints. Nonetheless, we feel that these limitations are not substantial enough to drastically alter the results that we receive, and the general themes of low deflections will still hold true. We are confident that our analysis presents an accurate representation of the expected behavior of the bridge under loading constraints.
All in all, the bridge design that Cornell Steel Bridge is presenting to you with today is a very solid design. The classic worn trussing combined with the sturdy space frame reassures people of the bridge's structural strength while maintaining a rich elegance at the same time. The bridge also fares well in both structural efficiency and construction economy due to the low deflections and construction-friendly connections, respectively. This is one upper truss bridge that will please the visitors of Katy Trail State Park for years to come.
We hope that this presentation was informative and highlights the benefits that our bridge design will bestow if chosen. On behalf of the entire Steel Bridge team at Cornell University, we wish to thank you for listening and hope that everyone remains resilient and healthy during these times.